Hello, this is Dr. Liu. In this video, we have a modified problem. This was from a previous problem that it has a gardener pulling a cart, and in that problem, he was barely able to get the cart to move, so he was moving at a constant speed. And in this problem, I modified it so that over here he is pulled against the effect of friction, slowly accelerates the cart at a constant rate. The rate we don't know, so it's no longer zero. Besides the force that I gave you in the unmodified problem, I'm giving you a frictional coefficient, which is 0.55. So let's see what we need to do in order to modify the problem and solve it. So previously we had already written down the force and its angle and also the total mass. These are unchanged. So what has changed is I erased the acceleration equals 0, so now the acceleration is an unknown. But I now know the coefficient of kinetic friction is 0.55. So I know this. And let's see what else I need to change. Maybe I should do this. Let me use a different color for the new things. UK is 0.55. So let's take a look at what else needs to change. We drew a diagram, a free body diagram. So let's take a look at the diagram. This force is still pulling, right? So that still requires the x component, the y component, the angle, right? And it doesn't really mention the exact magnitude or the angle. So even if the angles aren't the same and magnitude, this diagram still works for this force. And we still have a normal force up. The ground is still supporting the cart, and we still have the earth under our feet, so it's pulling with gravity. And then there's still friction, although friction may be slightly different. If you remember it, see, this was the frictional coefficient. So now with a slightly smaller one, I expect a slightly smaller friction, but I didn't really intend to draw this to scale, so that friction being there is enough. So this diagram does not need to change because we have the same four forces: a pull, angled force, friction, normal force, and gravity. Right, so this can just stay intact, which means this actually stays intact because this was that same force, same angle applied, that results in the same x component and the same y component as before the modification. And then over here we'll have to change because now we no longer have zero acceleration, right? So let's start erasing here. So this is no longer the case. And what's the case is now we know Fk, so we can change this Fk into mu k times Fn, the normal force. So let's do that. And this whole thing will have to change. So let's erase this. So now we have the x component, which is 737, minus frictional forces, coefficient of friction, times normal force. That's equal to mass acceleration. So 170 times a. I omitted the x because I know there's no acceleration in the y anyway. So that's our equation. We can call that equation 1. This equation came from the x component of Newton's second law. And now we have the y direction. Let's see what happens in the y. In the y direction, there is no change because there's literally no change in the formulation. Although things may have changed, well, in magnitude, these two forces still up, this force is still down. Even if I change the mass, I change how hard the gardener was pulling, then this exact formulation doesn't change. And there's still no acceleration in the y direction. So we still have the same exact thing right here. Let's get rid of this line here. And what this actually got us, let's put a number here for the y direction. What this got us was it got us the magnitude, this normal force, right? So we calculate for the normal force, which is gravity minus this x component of the pull, and we got this magnitude. And we already had that, right? So that is equal to this. And now I can calculate this this normal force. So now let's remove this. Now we know the coefficient was given this time, so 0.55 times the normal force, and now I can get rid of that. And I'm no longer asked about this, so I'll get rid of it. This is still a reminder, so let's keep that in mind. The coefficient of friction is a dimensionless or quantity with no units. So all I have to do is I calculate the Fk out, and I can replace this mu kFn, and then I can calculate and solve for acceleration. So I can certainly just do that now. Let me pop up the my Python calculator. So 0.55 times 1150. So the frictional force is 630, round to even, 632. So 632 newtons of frictional force. So now I can plug this into equation 1, but I definitely don't want to go to this line of equation 1. I want to bring this down. So equation 1 is 170A equals 737. This whole thing is 632. So the difference is over 100, right? 100 and 7 minus 2 is a 5. So that's how many newtons. And then I can divide both sides by the mass. So A is equal to the net force, 105 newtons, over the net total mass, 170 kilograms. And let's use Python calculator again. So 105 over 170. So we have an acceleration. Let's keep two sig figs, 0.62 meters per second squared. So 0.62 meters per second squared. And in an actual exam question, we could be doing either version, because I could ask you for acceleration, or I could ask you for another quantity while I give you acceleration, such as 0. I could also give you a non-zero acceleration, but I thought this is a nice modification. If you change the problem a little bit and you want to see where the changes have occurred, this helps you analyze what exactly is the structure, how you solve the problem. Will this change if a certain thing changes? And in this case, it doesn't change. The diagram stays the same. And what about other things? If the diagram stays the same, this will not change, right? So as I go down, I basically modify the problem, so now that I can solve for acceleration. All right, thank you.